Welcome back to our quantum journey. So far, we've explored how quantum gates manipulate qubits in ways that go far beyond classical logic. We've seen the X-gate, which flips a qubit between 0 and 1, much like a classical NOT gate. We've also looked at the Z-gate, which doesn't flip the state, but instead introduces a phase shift, changing how quantum states interfere. Today, we're turning to the Pauli Y-Gate, which combines the effects of both gates. The Y-Gate is unique because it both flips a qubit, like an X-gate, and also adds a phase shift, similar to the Z-gate. It performs a transformation that's inherently quantum. Its effect might seem subtle at first, but it plays a powerful role in how quantum systems evolve. Let's say that we start with a qubit in some general state, a combination of 0 and 1. When we apply the Y-gate, it swaps these components, but with a twist. The part that was in state 0 gets moved to state 1, with an added phase, and the part that was in state 1 gets flipped back to 0, also with a phase, but in the opposite direction. And what does that mean visually? If we look at the Bloch sphere, which helps us picture quantum states as points on a rotating sphere, the Y-gate corresponds to a 180-degree rotation around the y-axis. Starting from the North Pole, the qubit rotates to the South Pole and acquires a phase, which shifts how the state behaves in future operations. If you apply the Y-gate a second time, the qubit returns to its original state, just like a double flip. But in doing so, it also picks up a global phase. That might not affect the outcome of a single measurement, but it can have a big impact when you add more gates to the quantum circuit. In visual models like the state space or the phase disk, this transformation is shown not only by a change in the position of the balls, but also by a change in color, representing the new phase that the qubit acquires. These visual tools help us see how both amplitude and phase evolve during quantum operations, such as the Y-gate.